Hello, and welcome to class number 32 of Physics 218. So last time we talked about how one can make qualitative sketches of bound state energy eigenfunctions. We're going to apply some of that today when we consider the simple harmonic oscillator potential energy. And then we'll talk a little bit about why this is such an important potential energy for applications, and we'll specifically look at how this can be applied to molecular vibrations in chemistry. So the physical situation I would like you to have in mind when thinking about a simple harmonic oscillator is one you probably studied in Physics 217. So we consider a mass m on a spring with spring constant capital K. And here I'm going to use capital K for the spring constant so that we don't confuse the spring constant with the wave number lowercase k. Okay. And one more thing, I'm going to here define x equals 0. I'll set up my coordinate system to be where the spring is at its unstretched natural length. So you learned probably in 217 that this mass will oscillate with an angular frequency given by omega equals the square root of k over m. So, and you also probably analyze this from the standpoint of potential energy, the mass and the spring together forming the system, and the potential energy. Whoops. Of the system has the following form, right? You know that it's quadratic in the position x, or displacement from the equilibrium position. Goes like 1/2 big K x squared, and if you go and solve for k here, I can rewrite this potential energy, right? This is really just a spring potential energy in terms of m and omega, right? So if I solve for big K, if I square both sides, I get an omega squared, I get an m omega squared in the potential energy, so I get 1/2 m omega squared x squared. Okay. So let me erase the board, and then we'll think about what this means in quantum mechanics. In the quantum mechanical version of the simple harmonic oscillator, the goal is to solve the time-independent Schrödinger equation for the following potential energy, that is namely one that is quadratic in x, and I've sketched it for you here. Namely, what we have to do is to solve the following. The TISE becomes, okay, so we have our kinetic energy term as usual, d squared psi dx squared, but now we have our this potential energy plus 1/2 m omega squared x squared equals E psi. Now, right away, we can see that we have a little bit of a problem, right? For the infinite square well, right, we just knew that the wave function vanished outside the well, and then inside the well, the potential energy was zero. So we were able to turn the time-independent Schrodinger equation into just an oscillator equation that you know how to solve. For the finite square well, right, we had a constant potential energy, so at least piecewise, and we could apply a very similar technique. Here things are different, right? There's this term that has an x dependence, and this makes the time-independent Schrodinger equation here a lot harder to solve. Now, it is possible to solve this diffie-q. The solutions end up being in terms of what are called special functions, something called a Hermite polynomial. We're not going to get into the details of that here. We'll save those details for Physics 421. There's also a very elegant operator approach for solving the simple harmonic oscillator, which you'll probably also talk about in 421. However, we do have a powerful tool at our disposal for being able to sketch at least what the energy eigenfunctions look like, and that's to use everything we learned last time about qualitative sketching. So, hard to solve, but can sketch. So, what I'd like you to do now is to think about the whiteboard exercise I'm going to project, which involves trying to sketch the lowest few energy eigenfunctions for this potential energy. Now that you've had the chance to think about what the first few bound state wave functions might look like, let's use the PhET quantum bound states applet to take a look at what they actually look like, and I'll point out some of the important physical features. So let's bring up this quantum bound states PhET again. You've looked at it a bunch of times for other things, but you might not have played with some of the other potential energies you can use. So if I go and change the potential well to harmonic oscillator, we get the following. So notice that this is a potential energy that has even symmetry. And as usual, we can look at either the wave functions or the probability density. So let's start with the wave function, right? So as we might guess, right, for the ground state, right, so we have no nodes, so we have no axis crossings of the axis in the wave function. We know that this potential energy has even symmetry, right? It's the same reflected across x equals 0. So we would expect the energy eigenfunctions to be either even or odd. And in fact, we do see that psi 0 is even. It turns out that this has the form of a Gaussian function. I think you can find the first couple of energy eigenfunctions tabulated in Townsend. So let's jump up to the first excited state, which happens to be psi sub 1. So notice that this now has odd symmetry, like we might expect. I can toggle to seeing the probability density here, where we squared everything. Sort of notice is a feature we've seen in a few other in like the finite square well. Also, right, there's no in this energy eigenstate, there's zero probability to be right at the center of my well. So you can kind of see right here so here's E1, right? sort of the classically allowed region is sort of between here, it's like between here and like there. You can kind of see how there's this like decay exponentially in my forbidden region, just like we talked about there would be, and in contrast, how there's sort of oscillating behavior of the wave function in my classically allowed region. So some interesting things to think about, right? So if we go up to the to the second excited state, so that's psi 2. Let's go back to the wave function here. So once again, we see the same general behavior. You might be able to notice, right, that the some things about the amplitude here. So if I go and if I plot the probability density, that's probably easiest to see, you might notice that the amplitude is actually a little bit larger in these two side bumps than right in the middle. And if you look sort of at the width of this bump, you might be able to convince yourself that these side bumps are just a little bit wider than the one in the center. Well, that's consistent with everything we talked about last class as well, right? Because we talked about how as the difference between E and V gets smaller, so as V gets larger in this sort of allowed region, our wavelength tends to increase, as does our amplitude. So we're seeing that here, and maybe we can see it even more clearly if we go to a higher energy. If we go to let's say something like psi 6 or 7 with a few more bumps. Again, you see these edge bumps have a larger amplitude than the one in the middle. So okay, so anyway, so as you can see, that's our ground state, our first excited state, and our our first excited state, and our second excited state. And let's point out the node crossings as well, right? So notice how here we have exactly one node for our first excited state, and for psi 2, our second excited state has exactly two nodes here and here. So again, this is all consistent with everything we talked about in the last class. And you should run this FET and sort of play around with this and take a look at the wave functions and probability densities, play around with changing the potential energy, for instance, like I could tune the offset or change the omega associated with this oscillator if we wanted to. If you go through all the work of solving the time-independent Schrodinger equation for a simple harmonic oscillator, you will be able to show that the energy eigenvalues have the following form. They go like E sub n equals n plus a half h bar omega, where n is an integer that counts up from 0. So a few remarks here are in order. So first, qualitatively, right, it turns out that the energy eigenvalues for a simple harmonic oscillator are evenly spaced. So if I were to sort of sketch those energies on this graph here, they might look something like this. So if so that might be my E0 and E1 and my E2, and I'll draw one more here, right? So, so this now is quite different behavior than what we saw for the case of, say, an infinite square well. Right? Remember that in the infinite square well, the energy eigenvalues go like n squared, right? So the energy levels get further and further apart the higher up you go in n. In contrast here, the spacing is even. Energies are spaced evenly. Okay. Another sort of tricky thing about the simple harmonic oscillator energies is that you start counting from n equals 0. Careful. So for every other potential energy we've looked at so far, so for the infinite square well, for instance, we started at n equals 1. The convention that we start here with n equals 0 has to do actually with the special functions that give rise to the energy eigenfunctions, those Hermite polynomials I mentioned earlier. To sort of match the conventions for those, we have this convention that we start at n equals 0 for the harmonic oscillator. There's one other thing that I want to point out, which is a similarity between the simple harmonic oscillator and either the infinite or the finite square wells. Notice that there's also a 0-point energy. Namely, the energy of the ground state, right, E0, is not 0. Rather, it's h bar. It's a half h bar omega. And maybe I'll label that spacing here actually. So we have a spacing here of h bar omega.